In screen 6 of the simulation properties, we have two triangles, one of which is dilation of the other, and the center of dilation is point I. So you can see that as we change the scale factor, that I, H prime, J prime, the larger triangle, increases in size. When scale factor is less than 1, it's smaller than the original triangle. Notice that we have the three sets of sides here. We have IH, we have IH prime, and we have HH prime. When we look at the calculations, what we see is that the ratio of IH prime to IH is the same as the ratio of IJ prime to IJ is the same as the ratio of HJ prime to HJ. They're all going to be equal to the scale factor. And that makes sense because basically what we're saying is that IH prime here is the length of a side on the dilated triangle, whereas IH is the corresponding side on the original triangle. But we also can look at these side ratios here. So what we see is that the ratio of IH prime to IJ prime is the same as the ratio of IH to IJ, which is the same as the ratio of HH prime to JJ prime. And you can see that that holds true even as the scale factor changes. You can also see that those ratios remain constant. They're equal to each other, and they're always equal to 0.82. Now that changes, of course, if we change the triangle, because the particular side ratios of one side to another, well, that will change as the shape of the triangle changes. On the other hand, the scale factor ratio doesn't change as we change the shape of the triangle. Screen 7 gives us an opportunity to use a similar triangle to figure out the height of this pyramid. So what we see is that this pyramid casts a shadow, which is equal to, we'll say, the distance from this black dot all the way out to this blue dot here. Meanwhile, we have a measuring stick right here that goes up to the top of the red dot there and has a length of 5 meters. When we find the length of the shadow that the stick casts, it's 12.3 meters. The calculation we can do then is that the ratio of the height of the pyramid to the length of the shadow of the pyramid is equal to the ratio of the height of the stick, which is 5 meters, to the length of the stick, 12.3. So the three things we know are the pyramid shadow length, 150 meters, the height of the stick, 5 meters, and the shadow of the stick, 12.3. When we set up this ratio, we then multiply both sides by 150 to get that the pyramid height is equal to 150 times 5 divided by 12.3 is equal to 61.01 meters. Now notice that as we change the size of the measuring stick, the calculation changes, but because we're still talking about two similar triangles, we end up getting the same calculation for the pyramid height. So we're using the fact that this little triangle here and the larger triangle are similar to each other, and we use those ratios to figure out the missing piece, which is the height of the pyramid. In screen 8 now we're looking at a very special kind of right triangle. It is a right isosceles triangle. It has two equal lengths and the hypotenuse, and it's also equal to half of a square. The side lengths of this are equal to x, and x times the square root of 2. So for example, when the side lengths are 1.2, the length of the hypotenuse is 1.2 times the square root of 2. As we change the scale factor, let's say to 3, then the side lengths are now 3, 3, and the hypotenuse is 3 times the square root of 2. Well, suppose, for example, that we want to do a little more complicated calculation, where let's say that the hypotenuse had a length of 10. Well, if the hypotenuse is equal to 10, that means that x times the square root of 2 is equal to 10, and x would be equal to the length of the leg. So we set up the equation. X times the square root of 2 is equal to 10. When we divide both sides by the square root of 2, we get x is equal to 10 divided by the square root of 2. When we multiply top and bottom by the square root of 2, we get x is equal to 10 times the square root of 2 over 2, because the square root of 2 times itself is equal to 2, and that simplifies to 5 times the square root of 2. The other kind of special triangle that we've seen is the 30, 60, 90 triangle, which is half of an equilateral triangle. So let's say that this side on the bottom is equal to x. This is half of the original side of the equilateral triangle, so that means that this side here is equal to 2x. Well, the side right here is equal to x times the square root of 3. So, for example, when x is 3, then the height of the triangle is 3 times the square root of 3, and the length of this side is 6. And as we change the scale factor, everything changes, but the ratios stay the same. So when x is equal to 4, the height is 4 root 3, and the hypotenuse is equal to 8. Well, suppose, for example, that we knew that x was equal to 10, that this leg here was equal to 10. Well, that would be easy to do all the calculations. We would just multiply by 2 to get the length of this side here, so that would give us a hypotenuse equal to 20. And we would multiply by the square root of 3 to get us the height, which would give us 10 times the square root of 3. On the other hand, suppose that the height is equal to 10. Well, that means that x times the square root of 3 is equal to 10. So to figure out what x is, we have to divide both sides by the square root of 3 to get x is equal to the 10 over the square root of 3. X then is equal to 10 over the square root of 3, but we multiply top and bottom by root 3 to get this radical out of the denominator. This gives us x is equal to 10 root 3 over 3. We then multiply by 2 to get the hypotenuse, which is equal to 2x, is equal to 20 root 3 over 3. When we get to screen 9, we see the basic setup for the trigonometric ratios that we've looked at. So let's say that angle L3 here, or L, is the reference angle. That means that the ratio of the opposite side, which is side over here, 5.14, to the hypotenuse, 8.57, is the sine of angle L3. That gives us 0.6. The cosine is 6.86 divided by 8.57, and the tangent is 5.14 divided by 6.86. We see all these ratios here. Notice that as the scale factor changes, we're not changing the angle measures, so we're not changing these ratios. The sine of angle L, the cosine of angle L, and the tangent of angle L remain unchanged, even though the side lengths are changing, but the ratios are not changing. The same holds true when we're talking not about angle L, but about angle N up here. But now, this side here, the 5.71 side, is the opposite. So now the sine is equal to 5.71 over 7.14. Before, 5.71 over 7.14 was the cosine of this angle here. So the cosine of angle L and the sine of angle N are equivalent. The sine of angle L and the cosine of angle N are equivalent. The tangents, meanwhile, just flip. 5.71 over 4.21, 4.28 over 5.71. Screen 10, we look at a typical application of using the tangents. Suppose that we have the sun up here in the sky, and it casts a shadow of this building, and we know the shadow is equal to 130 meters. We also know that this angle of elevation is equal to 25 degrees. So if we look at this right triangle right here, we have, we'll call this h. That's the height that we're looking for. We have this side is equal to 130, and we have this angle 25. Well, with reference to this angle, we have the opposite side and the adjacent side, which means the tangent. That means that we have the tangent of 25 degrees is equal to h divided by 130. We also know from our calculator that the tangent of 25 degrees is equal to 0.47. So now we know that h divided by 130 is equal to 0.47. We multiply both sides by 130 to get that h is equal to 61.1 meters.